All right, that was a short break, and we're back for the second talk today. It's my great pleasure to introduce Dr. Jebb Stewart, who is the Chief of the Informatics and Visualization Section at NOAA's Earth Systems Research Laboratory. He's a pioneer in deep learning applied to satellite observations and will present today on pattern recognition challenges in the atmospheric sciences. Thank you, Jebb, for joining us. And I'll begin sharing your slides in a moment.
Great, thank you, Karthik. Yes, so I'm Jebb Stewart. I'm with the NOAA Earth System Research Laboratories, part of the Global System Laboratory. I have many collaborators on this particular project I wanted to highlight here. Christina Kumler, Isadora Yankoff, and David Hall from NVIDIA here helped with some of the projects we're going to discuss. Now, my affiliation is with NOAA. And because I'm with NOAA, NOAA currently has a policy that we're not allowed to use the Zoom software for presentations, but I'm allowed to call in. So for this, I greatly thank Karthik for stepping through my slides and assisting me with this presentation today. And since you won't see my face floating in the corner here, I decided to include my avatar in the introduction slide here for you, so you can see what I look like. So yes, today I'm going to talk about machine learning and segmentation for atmospheric phenomenon. So go ahead and go to the next slide, please. First off, I want to start with what is segmentation. So we've heard a lot of different talks about the different neural network structures, about how they work, about what's going on internally. We saw a little bit about this yesterday in terms of from David Hall about segmentation and classification, object detection. So this image you're going to see pretty often. You might see it in a couple other presentations, but you see here a couple different ideas in terms of segmentation and object detection. So in the middle, I'll start. You see there's a picture of a single cat in a red box there. So that is classification. There is a cat in this image, and the localization aspect of this is a red box around the cat indicating where that cat is in a particular picture. When we look at object detection, we can go a little bit further. We can look at multiple objects. We can look at dogs, multiple cats within an image. When we start talking about segmentation, we start to get into the area where we're talking about pixel by pixel where these objects are in a particular image. So on the far right, you'll see instance segmentation, where pixels for the individual dogs, red dog, there's a green dog and a blue cat now, have been highlighted to indicate where which pixels encompass those particular animals in the image. When we talk about semantic segmentation, it's the idea that every pixel is classified in a particular image. So here we see on the far left now, with that cat image, we see the pixels that comprise the sky, we see the pixels that comprise the tree, the cat itself, and the grass. And so the two here I'm going to focus on are mostly the semantic segmentation and instance segmentation. So where pixel by pixel in the images are the features we're looking for. Next slide, slide 3, please. So what's this look like for atmospheric phenomenon? So we have a couple different images here on the screen. Starting with the upper left is identifying an atmospheric river. So this is some of the work, we've seen this work with Karthik and the group at Lawrence Berkeley. We see where cyclones are in the upper right here. So highlighting the pixel by pixel where we think cyclone is in these particular images. We can do the same for other atmospheric features like hurricanes in the lower right. The middle image on the bottom is convection. So looking for convection in satellite imagery. And, you know, it doesn't have to be strictly from satellite. It can be any type of images. It could be from model data, forecast, outputs. In this particular case, we're looking at radar in the lower left here, and you can see the outflow boundaries. So being able to identify and segment these features are important. They're important aspects for what we try to do for some of our projects. Next slide, slide 4, please. So why do we want to do this? There's a couple different reasons. One is just simply identifying. So we have a lot of different data out there. Traditionally, it's been a manual process to go through things and identify and classify what might be in those images. Looking for features, you know, this isn't strictly for atmospheric features, being able to track the type of animal, if it's a polar bear or other things. And then there's kind of the aspect of tracking. So once we've identified a feature, being able to watch it through subsequent frames, you know, hurricanes or convection, see where those storms are going and where have they been. This can be used for early warning techniques. So being able to identify when convection is likely occurring, being able to identify those outflow boundaries. If we are able to sense those, we're able to pass those on to a mixed process or even a human to then send out warning for various products. We also look at this from a verification standpoint. So when we're developing an atmospheric model, we want to see how that model performs in various schemes. By schemes, I mean like if it's shallow convection, shallow cumulus, convection, clear sky, being able to classify, segment an image and say, these are the areas of these specific atmospheric conditions. We can then use verification techniques to look how a particular model is performing with regards to that specific scheme, that specific type of atmospheric condition. We also see a lot of this in terms of the automation of processes. So being able to detect and find where objects are in an image, we can move on to a next step. We can pass it on to a further process. This is kind of highlighted with the last bullet here, or last item on this list, the targeted data extraction. For example, if we know where areas of active weather are, if we know where cyclogenesis is happening, if we know that's where storms are forming, if we know where convection initiation is likely, we can identify those areas and further extract more information, ignoring other areas where weather may not be occurring or where we may not be interested. There's also a huge aspect in terms of climate here, in terms of analytics. So looking at forecast runs for climatological reasons, we can count and compare the number and size of features. A lot of this work is to see, how the model or how our climate might be evolving, and looking at the performance of these different climatological models. So we have a variety of reasons we're looking into segmentation. There's a couple different aspects here. So the next slide, please, slide 5. When we talk about segmentation, a big aspect of this is preparing your data. Part of preparing your data is the creation of labels here. There are a couple different ways we can prepare labels, and by labels I mean we talk about that segmentation again, the pixel by pixel classification or pixel by pixel identification in those images of where these features are. And so we have a couple different methods available to us. One is hand-drawn. This is, we see this through a lot of different programs right now, where we have experts looking at an image, identifying where is a hurricane, where is an atmospheric river, where is a mid-latitude low cyclone, and drawing pixel by pixel bounding boxes around that to highlight where those features are. This is subjective. We are looking at a visible, or we're looking at a satellite image, and we're identifying pixel for pixel where these can be. There can be a lot of confusion, or not confusion, but a lot of potential disagreement between what these labels might comprise for those features. Where is that atmospheric river start? Where does it end? Where is its edges? Our objects tend to be more fuzzy than a particular cat or dog. It is also very manual intensive. Requires a person to sit down, look at these images, go through each individual image and highlight the different features in it. If you're looking for multiple features, such as an atmospheric river or cyclone in the image, you're going to be drawing multiple shapes on this particular images. Another method is called heuristics, where we use rule-based. So if winds change direction by a certain degree, if the pressure is a certain value, those all combine into a criteria. They become objective-based rules to define where our features are. This can be fast because now a computer can go through and self-annotate and self-segment these images for us. But there is a chance we might miss some of the features, and there's also a chance we include erroneous features where they may not exist. Our heuristics may be well-defined, but it may not be completely inclusive. But heuristics, they may not perfectly capture everything, but they may be good enough for what we need. And then, from a machine learning standpoint, it can learn from these features. It can identify what comprises a majority of them, and it can, in some ways, outperform our experts for some particular features. Another aspect for creating labels is crowdsourcing. So we see this a lot with the Carthix project. They created, I believe it's ClimateNet, I might have that wrong, where they have a tool out there where users can participate and outline atmospheric rivers, outline hurricanes, outline cyclones. They give them instructions. They say these are the features to look for, and then using that information, they can aggregate a lot of information from users here, put that together to generate labels. So we have a couple different methods. Each have their strengths and their weaknesses, but these are some of the practices we have available to us. So next slide, slide 6, please. So when we talk about labels, there's a discussion about how precise you need to be. So we talked about when a scientist outlines a particular feature, there may be disagreements on where a low cyclone starts, where it ends, how much of that to include. With atmospheric rivers, we run into a similar condition here. So when we talk about exact, there can be some disagreement even amongst our experts about what comprises some of these features. Do we need to be a bounding box? Can we just simply draw a four-corner box around the feature area of interest? It's really up to the individual. What is your problem you're trying to solve? If you're trying to look for precise, if you need that precision, then that might determine what type of labeling system you use. If you have a little more leniency, you may be able to use a bounding box or other methods to segment your features out of a particular feature. Another question that often comes up is, if I have heuristics, why do I need machine?
It looks like we lost Jebb temporarily. We're going to try to get him to connect back in shortly. So please be patient with us. Hello, everyone. We lost Jebb on the line, and we're waiting for him to call back in so that he can continue the presentation. To kind of cover some other things on this slide, I think we left off with, if I have heuristics, why do I need machine learning? Okay.
I think I'm back.
Yep. All right, he's back. So thankfully I wanted to get the presentation for you. So
thanks. Where did I get cut off? I don't know when I was disconnected. So
let's start with I think that if I have heuristics, why do I need machine learning, that section?
Okay. All right. Thank you, David. All right. Sorry about that, everybody. Technology is fun. So yeah, if I have heuristics, why do I need machine learning? So there are oftentimes our heuristics are derived from other data sources that are not our target data set. So what I mean by this is my group in particular, we're processing a lot of satellite data, but our labels we generate from other data sources. We use it from analysis fields for models. So we have information like pressure and vorticity and winds. Those allow us to create high resolution, better labels that we can then apply to our satellite data. So we use heuristics to get those labels, but our target data set may not have that information available to it. The other aspect here is that heuristics have a lot of information that can go into them. They can comprise many different variables. It can be a little bit slower, but once you have a machine learned model with those same labels, the inference stage, the prediction stage is very fast, where so it can be significantly faster than the heuristic data set. So there are a couple different options here why we look at heuristics to help generate our labels and not use them specifically by themselves. So next slide 7, please. So what does a label look like? When we're labeling information, we need to convey to the machine learning algorithm where these features are in a particular image. This can be as simple as a binary mask using an integer encoding method. So in this case, on the left here, you see we have a circle that indicates where a hurricane is in this particular image. The array below is a representation of what this would look like in, say, a NumPy array in Python. where that hurricane circle is in this particular image. So we see a bunch of zeros where there's no hurricane, and then the ones indicating where the hurricane itself is in this particular image. And if we have more than one class in an image, we can use, using this integer encoding method, we can add other numbers. And so we often see this for a variety of data sets here. So on the image in the middle here, then we have, this is just mock-up information. This isn't from an actual case. I drew a purple shape around a cloud more towards the right of the middle image here. And so we can see in the array below now, we have ones to indicate where in this image the hurricane is, and twos to indicate this cloud shape I've identified by hand in this particular image here. So if we're looking at this from a machine learning standpoint, our number of classes here is n, but our labels, I guess the error here, but it's an array of x by y, and then it's a single value, and that single value, actually, maybe that's correct, sorry, I can get confused myself here. And go from 0 to n in terms of the number of classes in this particular image. Next slide, please. So this can be used. It depends on how many classes you have, but there's a problem here in that the model can interpret the values order as something meaningful. It could say that higher numbers have a higher importance. This is something we don't necessarily want for our machine learning model. It can imply, it can imply order or meaningfulness to this array. So next slide. There's another method called one-hot encoding here. So this is where now we can look at this information from the middle image we had before. We had an array that had indexes from 0 to n in terms of what is in that particular image. And we split this into the individual arrays for each object we're detecting. So here we split into 3 different arrays. We have the background. So where is the background? So we indicate ones indicating where all the background is, and zeros where it's not the background. The next array is where the cyclone is. So we have the same shape as on that first slide where we have zeros, and then we have ones in the middle where was the cyclone. The last array here is a cloud. So where was that cloud again? So we're not going from 0 to n in an individual array, but now we have n arrays indicating where those specific features are in each of the arrays. So in this case, our ending array becomes a label of x, y, and n in terms of the number of classes we're trying to solve. So this is how we can look at separating that importance, that hierarchy, allow the machine learning model to determine what these features are. I would say that you don't necessarily have to do this yourself. You can create an initial array that has the 0 through n in it itself, and there are a bunch of variety of tools within the Python library that can split this into a one-hot encoding for you. So you can either do it by hand if you prefer, or you can do an individual array that can be split later for segmentation for your purposes. Next slide, slide 10, please. So in terms of our data, we have dataset challenges we often see for segmentation here. So an example here is we have a water vapor image from the old GOES imager series here. It's been color coded, this I think is channel 3. And on the right is this same water vapor image with tropical cyclone labels. So there's a data set called IBTrax. There's a link to it at the end of my presentation here, which has a historical record of where tropical cyclones are across the world. So using this information, we're able to label the particular data set. And so you notice that the boxes here, there's just a handful of them, there's 4. And this is a particularly active time period where we have 4 individual storms. So if we move to the next slide, we'll see why this is a problem here. So slide 11. So on slide 11, we see that the label, the truth, is we have kind of a binary mask, black indicating where there's no tropical cyclones, and white indicating where there are tropical cyclones on that particular image in terms of this array. If we get a prediction from the model where it says there's no cyclones at all in this image, because these boxes are so small, this can be interpreted as 95% accuracy. Hey, we're doing pretty good. But that's not the case because we're not actually doing the active detection here. And so understanding your problem again, understanding your data set, understanding your labels is important when we look at segmentation here. So what is the information we're trying to find? What is it, how we're trying to extract it from this image? And then, in terms of the model, it's going to try to optimize its accuracy, optimize its loss function here. And it can do that by saying, hey, there's no tropical cyclones in this particular image. So what are some ways that we can get around this? Next slide, please, slide 12. This is called a dataset imbalance problem. So we have very little of the image we're actually actively segmenting that we're trying to extract. So we have a high number of one class, which is our background, we have our minor class, the tropical cyclones, is a very small value of the overall pixels in this particular image. There are a couple different techniques. Two I was going to focus on for this presentation were image processing techniques. And also there's a variety of different loss functions out there that you can use for looking at image similarity. So this graphic I came across, which kind of captures a lot of them. You can see there's a bunch of different ones. We'll get to two of these in detail here as part of this presentation. So moving to the next slide, slide 13. So this is, the one technique is image processing. So here we have a cyclone indicated in this particular panel, kind of lower central image here. We can extract individual images from this series. So we can get ones that include a cyclone, as well as images that don't include a cyclone or include partial aspects of that cyclone. So now since we have a series of images, we can make a more equitable distribution of both positive and negative segmentation here. So there are some potential downsides. There's a lot of processing. Once you construct this, you have to put it back together. And once you do the prediction, you have to put it back together. It's not as efficient. But there's also the aspect that in the neural networks themselves, when we look at the kernels and convolutional layers, this is happening internally to our neural network structure. And so we have those kernels that move across the image that are extracting these different capabilities. They're doing this for us. And so it's not necessarily an efficient process, but it is one way we can help this dataset imbalance problem. Another way we can look at this is our loss function. So moving to slide 14, next slide, is that we can use different loss functions that evaluate the images differently for us. So one that we use in our work is the dice coefficient. This is an intersection over union type evaluation. So where do our labels overlap? So we have a truth and we have a prediction from our images here. So in the first image, our first set of boxes on the lower left, truth is in the dark blue, prediction is in that lighter blue turquoise frame here. And where they overlap is where we're trying to increase this intersection over unions. We're trying to get the most overlap between these two shapes as possible here. So in a dice coefficient, we look at this in terms of the intersection over union. So if we have complete overlap, identical images, our dice coefficient becomes 1. If we have no overlap, if those two boxes have no overlap at all, our dice coefficient drops to 0. And so we can do this across our entire image here. And we have different aspects of this in terms of, so you can look at the blue, and we'll move into the graphic on the right here. The darker blue is the areas where we have false negatives. So this is where the model did not predict a feature, but the feature did exist in our label truth set. In the lower right, we have that turquoise, that lighter blue color again. It's our false positive. So this is where our model predicted a feature, but the feature did not exist itself. And then we have the true positive. So this is where they do overlap, is in the middle. So we're trying to increase the amount of our true positive. Again, if we get our dice coefficient to 1, this indicates we have an exact match. So to turn this into a loss, you can just take 1 minus the dice coefficient to turn it into a loss function. We can look at what this looks like in code here. So we go to the next slide, slide 15. We use Keras and TensorFlow for our libraries, for our work. This is what the dice coefficient looks like. So we get the true, our true values, which is a 0 to 1. Our prediction values, we flatten these arrays. We look at the intersection between these two and we add them up. And we divide that by the total sum of the two from both parameters. So again, if we have our intersection is smooth is the same values, we have it'd be basically the same number on the top and the same number on the bottom. We have this smooth variable here, which helps the optimizer, helps shift it a little bit to improve how the TensorFlow handles this loss function. It also helps us avoid a divide by 0 problem. So if we can offset it by a little bit, we can help the smoothing factor here. And you can see in the middle here, we can turn this into a loss by taking 1 minus this particular value. So here's an example of us using dice coefficient and scoring that to improve our accuracy for our overlaps for image. So moving to the next image, our next slide here, slide 16, there's another loss function we can use called Tversky coefficient here. Tversky coefficient is a way of weighting a particular value more than others to kind of, in this case, we're going to penalize our false negatives more. So in one of our projects, we are more interested in areas of active weather, so where cyclones are forming, or cyclogenesis, or just in general what we consider maybe a region of active weather, because we use that for another process where we want to extract more information from that. So for us, we're okay with more false positives, because in our case, it may be still an area of active weather that we can use for further processing. But we really want to minimize our false negatives. And so through this process with the Tversky coefficient, we can use these weighting factors, these alpha and beta factors, to weight our false positives and our false negatives here. So you can see in this equation, we have the intersection over union again. We have this added element of the alpha times, so X being our truth, Y being our prediction. So the first alpha is the X minus Y in this case is our false positives, and our Y minus X is our false negatives. And so by having the beta value be higher, 0.7, we're adding more influence on our loss function to make this to weight our false negatives more, and try to, when our loss function is performing as part of our neural network here, we hopefully get a better result because we're able to penalize those false negatives more than the false positives. So moving on here, next slide, slide 17. I'm going to move on to kind of discussing some of the neural network structures for these features. So one of the common ones we see for image segmentation challenges is the UNet structure. So UNet is a type of deep neural network structure where, and you heard David Hall discuss this a little bit yesterday in his NVIDIA conversation, where we have these skip connects, which take features from the upper part of this U, and it's both a, so we take features from the upper part of the U here before compression. So when we look at this in terms of a neural network, we have the first three lines we have in the upper left of this U. You have your input image, and you have two convolutional layers here. So the skip connect takes the information from the first two convolutional layers and applies it to the last layer here. So it takes information about the full resolution of the data before any pooling or any compression, and moves it over and has it part of the end here, the deconvolution, where we're looking at our end results here. The red arrows going down are part of our max pooling, where we do it's basically compression. So we do a 2x2 max pooling as part of UNet, which basically divides the image in half in both X and Y dimensions. And we do the convolutional layers again. So one advantage of this for, especially I think for meteorological or atmospheric conditions here, is that we get a lot of our shortwave, our small features. We're able to capture that because we have a skip connect across the top of the U here before the compression. We also look at some of our longer wave features. So after we've looked at the compression here, we're able to capture some of our longer wave features. So using both our shortwave and longer wave features, I think for an atmospheric phenomenon, UNet works particularly well. This is not the only tool in the toolbox. There are a variety of other neural network structures that can work for image segmentation. This is one that's worked particularly well for us, and we see it in a variety of other image segmentation challenges. So we can look at this a little more in depth with some code here. So we go to slide 18. This is a Python block, again, using Keras, the Keras and TensorFlow, of what this convolutional 2D block looks like. So this is the first step in this UNet structure here. So you can see I highlighted, I chopped out the block here. So we have, if you look at in the middle image here, where we have the input image tile, the first layer is the image itself. So you see that this is a single channel. So it has one above the line there, and the image itself is 572 by 572 pixels. It's fed into two different convolutional layers here. So in the code, you can see for L in the range of 0 to the number of layers, create this convolutional with the number of filters here. You can see how you can apply batch normalization after each layer if you wish, and then they have an individual activation after each convolutional block. And so we repeat this twice for each step in the UNet structure here. So this is also a chance to talk about your channels for inputs here. So if we have a grayscale image, that's just an order from 0 to 55 or whatever the values might be, the input into this UNet is your batch size, and then the X by Y. So 572 by 572 is indicated in this graphic here. And then the number of channels, in this case, it looks like a grayscale, so it'd be 1. If you had an RBG or RGB image, three channels here, you within that last array item would increase to 3. But you're not limited to 3 here. You can do any number of channels you want to send into this. So it depends again on your problem you're trying to solve what you're trying to look into. At a certain point, it may be beneficial to look at the 3D convolutionals, where you go across the 3 dimensions versus just the 2 dimensionals here for this layer. So the next slide, as we start to go down the left-hand side of this UNet structure, we look at this contracting path. So we have these convolutional blocks up together. So we have the convolutional followed by a max pooling, which is the compression. You can apply dropout here if you like. This is a pretty high dropout value. And then you can do the next step, the next block. So you create 2 convolutional layers, a max pooling, and a dropout. And you can repeat this through the structure you use. So in this case, we have 5 different layers. In the last block, you see our convolutional layer that puts this together. So the important thing to note is that in the traditional UNet structure, the number of filters is increased by a factor of 2 after each compression stage. So it's going to I'm highlighting on my slides, so that doesn't help you because I'm on the phone. When you have a max pooling layer, this is that compression stage. So you're taking each 2 by 2 box is consolidated to a single pixel. So that's where you drop your dimensions in X and Y by a factor of 2 in each way. So if you had a 512 by 512 image, a max pooling with a 2 by 2 array, you'd end up with a resulting of 256 by 256 image. And so that's what I mean by compression here. So the max pooling results in a compressed image that's now 256 by 256. If you do it again 2 by 2, you drop it to 128 by 128 and so forth. And so we're able to increase the number of filters for each of these layers because we have smaller input data. We can look for more capabilities. We'll get to this some discussion about some modifications you can make to the structure, but that's kind of the general sense of what's going on. Then we get to the expanding path. So if you go to slide 20, we're looking at the expansive path here. We do the opposite now. So we do a convolutional 2D transpose, which enlarges our image. So this is where we do an up convolution, where our 128 by 128 will now expand to a 256 by 256 image, and then we keep repeating that till we get back to our original shape. So we do these convolutional 2D blocks again, followed by this upscaling to our data sets, and eventually get back to our original segmentation map size here. So you can see at the bottom here where our outputs, our eventual layer is a single 1 by 1 convolutional to our output segmentation map. And then our model is comprised of our input and output, our arrays of our inputs and outputs here. So important to note on this side is that we decrease our number of filters by 2 as we go up through the scale. So you can see that we go from 8 to 4, and then we go to 2, and then to 1 as we go up through the expansive path of this particular UNet structure. And so that's kind of the code that goes around a UNet. You can find many examples online, and I have a tutorial linked in the notes here if you want to step through it and Python notebook on your own. So a couple things to consider going on to the next slide here, slide 21, discussion on neural nets for segmentation. We have a couple different things to try. So in this particular example I showed you, in the default structure that was in the paper that originally developed the UNets, they used the dropout function after each of these convolutional sets of convolutional blocks. You could look at applying Gaussian noise instead of the dropout. You can also look at things like varying your number of filters in a value. So you can start with a higher value, you can start with a less value, so like 16 or 32 in terms of the initial one each time you're doubling those number of filters. So what are the different kernel formats you're looking for in each of those convolutional layers? There's also a case to be made that you can keep your number of filters consistent between these blocks. So rather than multiplying by a factor of 2 each time, you keep the number of filters consistent. Because if you're only looking for 16 filters through each convolutional layer, that may be sufficient for your problem. So depending on memory, depending on other parameters, the other things you're likely to be looking for, these are things you might consider, might try to improve your accuracy for your particular problem. Another thing you could try is varying the depth of your UNet. So we showed an example here where our depth was five layers. We had C1 through C5 and then an expansive path back up. You can make these deeper, you can do more convolutional layers, or you can make them more shallow, depending on what type of capability you're looking for. Another option is to vary your final activation. So in this particular example, our final activation was a sigmoid, which forces it to 0 to 1. You could look into other ones. You could look into ReLU or some other final activations here. And again, depending on what problem you're trying to solve, could be important for improving your accuracy for your network. Looking at things to consider here, the depth and the number of filters do have a significant impact on the memory usage. So you may be limited by what's on your GPU or your system here, you may be forced to change some of these parameters in order to fit what you have available to you. So these are some options to consider. The other thing, as I mentioned before, when talking about UNets, is that this is one of many deep neural networks for image segmentation. This is something we found to be very useful for our needs, but you may want to look at some other UNet structures. I believe one David mentioned yesterday was the Deep Lab version 3. They have a couple different versions there, and it's very useful for image segmentation as well. So there might be other implementations. Next, I'd like to get into some real-world examples of what we've used this for. So on slide 22, the next slide, we have our UNet in action. So this is looking at tropical cyclones on satellite imagery. So this was using the old GOES imager. So this is the previous generation of satellites, not the new GOES-R ABI imager. We were looking at the water vapor channel for this particular image. For our labels, we use this data set called IBTRACS, an International Best Track Archive for Climate Stewardship. It maintains a list of all the tropical cyclones around the world for many years, for maybe 50 plus years or more. I forget how many years are there, but we have significant data. And it's kind of the trusted source of record for tropical cyclones here. It has information on wind speeds, the max wind speed, as well as in some cases, the radius, so how big those storms are in particular. We had data for several years, from 2008 through 2016. This was split in the train, test, and validation sets. They were distinct years, so we didn't have any neighboring cells within the train, test, and validation. We wanted to try against different years. For our cases, because we didn't have consistent radius information for some of these storms, we decided to use a box, so a 25 by 25 pixel box on these particular images here, centered over the storm. You'll see kind of the impact of that here when we get to an animation. And for our storms, we looked at only the form storms. What was classified as a tropical storm or greater on the Saffir-Simpson scale, which was 34 knots or above. And for this particular case, we had around 10,000 label data sets we can use for our training purposes. So moving on to the next slide here, you're going to see an animation. On the top is the manual labels that come from the IBTRACS. On the bottom is the automatic labels from the results of our neural network trained, the trained results here. So a couple of interesting things to note is that we did use these 25 by 25 pixel boxes as our labels. And so the neural network picked up on that and would also use a box for its label in the end result here. Sometimes you see that the edges of the boxes are trimmed. I wasn't quite confident on those levels for the entire box. But for the most part, we see the same boxes we had as part of our training set. And so this is important to note when you're looking at segmentation. What you send in, depending on your accuracy, depending on the problem you're trying to solve, is going to be very similar to what you get out. So important to note here. The other aspect is that you see a lot of interesting features on the oblique angle, so the edges of the satellite image here. So we see a lot of false positives where features might pop up on our labels. But for our purposes, for this particular problem, we were looking for regions of interest. We were looking for areas of active weather. We were looking for cyclones that would be passed on to the next step, where we further extract information, extract data from these things. We can also, so we can target the ones that are in the center of these images, and we can move to another satellite view. So we can move from GOES east to GOES west to get more center. We can ignore those ones on the oblique angles. So for our purposes, this is sufficient enough for our results. So it shows cases something what our UNets can do for these structures. It showcases some of what are the impacts of our labels and some of our choices. And for this, we were using that Tversky coefficient, where we were weighting our results here to kind of get across some of that data imbalance problem. Moving on to slide 24, another aspect we use our UNets for is looking for areas of convection initiation from satellite imagery here. So this is stepping slightly into kind of a predictive capability, because we're trying to look at a satellite image, and based on the current conditions, where do we think convection is likely to occur in the future? But it's not entirely based on prediction, I would say, because there's existing algorithms that have been developed both on the old GOES imager, the previous generation series, from John Mikolajkowski. He developed an algorithm against those parameters strictly in the satellite data. And then against the newer GOES imager or ABI imager series, there was a new algorithm he developed against that. So to do something similar. So looking at conditions in these satellite images using the different bands available to us, the newer image, new GOES imager, the new GOES imager, We now have 16 bands or channels of observations available to us. There's a lot of information that we can convey or we can extract from those different channels that we can use to find areas where we think convection is likely to occur. So what does this look like for our generating our labels? I'm going to step to slide 25 now. So in this particular case, we are trying to get a 90-minute lead time. What this means is that we use data up, our T is the current time. And so we use data from the satellite up to 90 minutes prior. So we are including temporal information in our convolutional layers by using multiple time steps in those different channels. So I talked about this before when we were talking about the UNet structure, that we can use channels in terms of the RGB of an image. We can also use channels in terms of just using different time steps in those specific channels for the for our data set here. So in this case, we have two different bands, band 9 and band 15 we used. And we used 3 time steps for each. We used T minus 90, T minus 100, and T minus 110 minutes here for these images. So we have a little bit of temporal information along with the geospatial information for these particular bands. We used the radar image to generate our labels. This is a heuristic-based rule, so it's generally accepted that 35 dBz is where we have deep convection occurring, or we have convection occurring. And so by using this threshold, we're able to create a binary mask of where convection is occurring in this particular image, so at time t. So we have, overall for our model, we have 6 input arrays, those the 3 time steps for each band. And our output is a segmentation image, a binary mask of where dBz is greater than 35 dBz. If we step to next slide, 26, we will see an animation of this. First, we're going to start with T minus 30. And so as you watch this particular frame here, you can see that there's fairly good agreement. You know, I don't have any statistical numbers here about the accuracy of this, but from a visual standpoint, you can see that overall the model is indicating areas where convection is likely to occur with a lead time of 30 minutes. The one problem with using 30 minutes here is that there's a delay for when we receive the satellite information. So usually there's a 10 to 20 minute delay. So in this case, if we're using a prediction for T minus 30, we only have a 10-minute heads up. So we want to try to extend this particular window. Again, for this image, the actual labels are on the left and the predictions on the right. If we step ahead to the next frame, our next slide on 27 here, we extend this time period out to the 90 minutes. This is what we talked about when we're preparing the data here. So again, the truth is on the left, the predictions on the right. So we're trying to extend this prediction period out as far as possible. There's a couple of interesting things to note is this hopefully loops, I can't tell, hopefully it's looping for you, but you can see it does pick up some particular areas where convection is occurring. It's able to follow the larger storm system, so it looks like the convolution network is picking up some of the optical flow of the direction that the storm is heading. And it is able to pick up some of the convection initiation, which we kind of call the popcorn, where there's new instances of convection that are now associated with that larger system. So there is some skill here that the system's picking up. It's a long ways to go. I think we can make better progress and improve upon this. But it is interesting to note what the neural networks can pick up here and see and do with the information we have. And this is some of the capabilities we have for our UNet structure. Moving on to slide 28. So in summary here, David John Gagne talks about this on the first day, that you really need to understand the problem you're trying to solve first, and then look at the tools available to help you with your solution here. So there's many different tools in the toolbox. I've showcased a couple here, the UNet structure, different loss functions.
Can we pause for a moment, Jebb?
Sure.
I'm sorry, there was a crash on the PowerPoint, so I need to restart it.
Okay. I'm having a good session, but the technology issues here. So. I can answer some of these questions maybe here while we wait. So, there's a question from Victor about how did you decide which cost function would be best to use? For us, it was more trial and error. So we took a look at how do these different loss functions perform for us. So originally, DICE was giving us pretty good results, but we wanted to see if we could improve it further upon that. So we looked at that weighted Tversky. We also looked at a weighted binary cross entropy function as well. And so that was more trial and error. So understanding our image, understanding our data sets, what we're trying to do. We had a couple of different losses we thought would work best for us. We also looked into something called a focal loss as well. And ultimately we decided we just, it was through trial and error, looking at the different loss functions, changing up and seeing what gave us the best results is how we ended up with the one we ended up using. So there's a question for Tom. Can you discuss the differences between deep learning architectures that produce one prediction per pixel versus those that segment on an image in a one go? I'm not entirely sure I understand the question here, but one prediction per pixel versus a segment of an image in one go. I'm sorry, Tom, I might need a little clarification on what you're looking for there. You can always email me too. Email will be here at the end. We can discuss this further if you have any questions. There's a question here about what image segmentation labeling tools exist to help mark up a data set. So there are a couple different tools. There's these, I believe I included it in my notes. I'm going to see if I can find it. So I don't know it off the top of my head, but there is a tool where you can highlight certain pixel classes and have it, you can paint on top of that and it'll separate it into your classifications for you. I'll have to see if I can find that and I can add it to notes here. So if you want to do it by hand, if you want to hand paint, there's the tool that Karthik and his team developed in terms of labeling atmospheric rivers and cyclones. So there's one tool that might be available for other data sets. And then there's another tool I saw where you can do something similar that will help it separate into classifications. I believe it's in one of my links here on the notes. I just don't remember which one.
Jebb, we're back on, so if you would like to continue with the slides.
Sure. So I've on the summary here. So it's discussing there's many different tools in our toolbox. So one for us, we found we watched a lot of the challenges on Kaggle in terms of image segmentation. We also see a lot of similar methods being developed for medical imagery. So we read a lot of papers on the different practices for image segmentation being used on medical images. It seemed very similar to the problems we were trying to solve. And so for us, we understood what we were trying to do, but then we looked at how other people are applying these techniques across different fields. So medical imaging, cars, other computer vision techniques. And based on their research, what their findings were, we experimented with those losses, with those dataset imbalance challenges for our particular data sets. Labeling data is a challenge. That's one of the questions that came up here. We don't have an agreement often amongst our experts of what comprises an atmospheric river, what comprises a mid-level extratropical cyclone. And our objects can have fuzzy edges. How close to the line do you draw? So again, this goes back to how precise do you need to be for your problem. So for our cases, we're looking for areas of interest, areas of active weather. We had a little more leeway on our precision we needed for our labels, but that may not always be the case. So it can be challenging. Being aware of data imbalance is important here because you can get look like really good results, but you need to plot your results and look at your results and see why your machine learning model is getting the answers you are. So data imbalance can skew those results. So you want to make sure you evaluate and look at random samples that you're getting the answers you expect, as well as take a look at these different loss functions or different data processing techniques to kind of help improve your data imbalance. This was I brought up many times by different groups here, but this field is rapidly evolving, and we're seeing new techniques every day. It's exciting, very exciting to see this, but it can be difficult to keep up. So watch the Abrix website for the new papers that come out. Just watch what people in the field attend things like this, the training and workshops, to see how other people are applying new technologies. It'll help you give you an understanding of what might work in your field and your expertise. So with that, my last slide is just my thanks. Thanks for the invite. Thanks for helping me with the slides, Karthik. And if you have any questions, please feel free to send them along, and I'll start answering some questions here. So first question I see on the top of the list here is, is sighting window going to produce lots of arbitrary images of objects that are really hard to label? Half of, e.g., is half of a hurricane positive or negative? So in this case, it's the same labeling criteria. You're taking the image, you have two different arrays. You have the underlying image you use that you're trying to predict from, and you have your labels already. So you use the same sighting window technique on both to subset, so you end up with the exact arrays. So you can have half an image that comprises half your hurricane, where you'll see the segmentation of that. And I think that's important because it allows that, it allows the hurricane to move through the different parts of the image here, so that the neural network can pick it up wherever it might reside. That said, I think that the kernel methods of a full convolutional network, without having to use the image sliding techniques, may be a better course of action if you can use other methods to account for the data set imbalance, because that's essentially what's going on in those convolutional layers itself. It's striding across the image, looking for those particular filters, the particular way the edges are aligned across the image, across every piece. And so it's looking for that automatically, similar to a sliding window technique. When you refer to heuristics, do you mean predetermined rules? Then ML is about learning those rules and maybe able to detect new ones. Is the question here. So this is true. So there's a predetermined set of rules. If A equals or is greater than some value, if B is greater than some value, it's determined that this is a front or atmospheric river or some other feature you're looking for. So these are based on predetermined rules. They may be, some of our rules may be comprehensive enough to include all our features, but in some cases, it's the best case to gather the most features for us, and it may miss some or it may include erroneous data. And so ML, machine learning, does, in a way, pick up those rules and learn those rules for you. And I think that's why we sometimes see that it improves upon that, because it's able to pick up new features that are similar, because it's not using those rules itself, it's learning those rules for internally. And so it's basically coming up with new rules inside the model to get from A to B. So we have our inputs are A, the results we want are B, and we use rules to say this is what we'd like you to find in B, but the deep neural network is coming up with its own rule set internally that is to determine how we get from A to B. And I think this is also part of this explainable AI too. You'll see some talks on later this week by both Amy and Emma to help kind of understand what's going on inside the neural networks here. What these rules, what are the rules it's seeing, and what are some of the correlations it sees in these data sets, and to help us better understand why it's getting the answers it's getting. For one hot encoding, do you have overlapping labels? That's a good question. So in an image, you won't. So you'll have a cat, it'll be front and center. Its edge of that cat will overlap or will come close to the next animal next to it, like the dog. And so you should label that what is in front there, so that you shouldn't have overlapping labels for one hot encoding, because you'll go right up to the edge and see the edge of that. So you might have half a cat, you might have half a dog as part of that, but you won't have overlapping labels. Can masks be Bayesian instead of binary, like a value between 0 and 1? Yes, so that's a different way to potentially solve this problem. So you'd have to change your loss or the final activation layer, because in this case, our UNet was using sigmoid, which will force the answer from 0 to 1. You could look at using ReLU to get probabilities. So there'll be some inherent probability in the prediction that's produced by the network, but you can also use these UNet structure to even do regression. So you can use a UNet structure to look at regression instead of segmentation, and try to predict actual values of some underlying feature. So we see this being used by other people as well. So it doesn't have to be 0 or 1. Depending on your problem again here, you might be able to use other values. But you'd have to change your neural network to understand what those mean a little bit. Has there been any comparison between AI-based convection initiation products and the NWP staff products and UMetSat? For our work, not yet. So ultimately, we want to get to a point where we're able to compare against existing algorithms. Right now, we're just exploring to see if we can improve upon existing techniques and seeing what skill, if we can increase skill. And at that point, once we understand the skill we're creating, we can compare against these other products that are being produced by other groups. This includes what we use potentially on our own Go satellite here that's been developed by these Go are proving grounds. I'm looking through the questions here. For MOS-like ML AI applications, are there examples that the application not only improve the skill scores, but also the domain knowledge, e.g. theory? It's possible. So we see this across the board that, even outside of atmospheric phenomena, we see that machine learning is able to better determine than humans potential segmentation, potential capabilities here. So it can not only improve the skill score beyond what humans are capable of, but it also could improve our domain knowledge about this. It could lead to more science. So I think this is more of an aspect about the explainable AI, and some of the talks we'll see later in the week here, but understanding what the neural network sees in these different layers through layer-wise relevance propagation or other methods. It'll increase our knowledge about what the neural network is seeing, and it could increase science around that. So we could explore that there's maybe not a correlation we saw before. It may lead to a scientist to explore that correlation further to understand the scientific process behind that correlation and increase our domain knowledge about what's going on there. So it's not just moss-like. I see a variety of other ways that we can expand our knowledge base based on these neural network structures. There's a question here about how you might systematically choose weights for Tversky coefficient. There's these hyperparameter search algorithms out there. You can explore the full space of the different weights. So there are ways that it's kind of a programmatic approach to go through and to see what gives you the best score for your test and train and validation data set. So there's tools out there that can do this for you, that can look through and explore the range of weights to choose what might be best for your system. So there's a question about the batch size in my slide 19. Batch, so when you create a neural network and you send, you don't, when you're training a neural network, your batch size is the number of images you send together in a grouping through a training phase through the system. So an epoch, let's see here, I might have to back up and I might run out of time. So if you have 100 images, and your batch size might be 10. So you're going to send through 10 of those images at a time through your neural network structure. It's going to backpropagate the errors, readjust the weights, and send them through the next 10 images, and do that over and over again. And at the end, that's one epoch when you've gone through all 100 images. So when I talk about batch size here, it's an indication of how many images we're sending through at a time. And we vary batch size. You don't want it to be too small, because then there's going to be a lot of shifting of those weights within the model between each batch size. But it's too big, and you might have too much information there, and you might not shift it enough. And so there's another balancing factor here. We talked about hyperparameter search to make that happen. And so you can explore different batch sizes. You might get different results for your algorithm. So it's just the number of images you send through at any one go as part of the training process. So there's a question here about how segmentation works in defining land use pattern. Is it possible? So yes, we see that. So USGS has quite a few different data sets that talk about land use. And you see experiments using satellite data to classify and better see to see those changes of land use over time. And so a lot of that exists out there. I don't have any exact papers I know off the top of my head, but if you search for some of this land use and some USGS data sets, I think you'll come across quite a few papers that discuss the segmentation and looking into land use. So there's a question here about how many of my 10,000 labels are independent, not the same cyclone, and how do you split them up into train, validation, and test? So in our particular case, I'm going to answer the last part first here. For our particular case in train, validation, test, the train data set was several years in the middle. So I had 2008 through 2016. Our train data set was 2009 through 2014. And then we took both years before and after that period as part of our train and validation. So the validation was in like 2008 and 2015, and the test was 2009 and 2016. And so we split those individual years. So there, for some of the long-lived storms, there can be subsequent the same cyclone. I don't know how many labels were independent, not from the same cyclone, but we covered many different years of data sets here. So we have several different years of storms. We could go back a little bit further, but then we start to get to older generations of satellites. We try to keep it in the same GOES imager series. We could also go forward looking at GOES 16, where we have much more frequent information, or GOES R, and you have much more or much less independence because you have more images of the same cyclone. That's not necessarily a bad thing. It just depends on what you're looking for. Could you please define what dropout again? So dropout, we use dropout. You basically set the values to 0. So you have a convolutional layer, which gives you some results, gives you some information, some numbers, and dropout randomly goes through your array of convolutional values and sets some of them to 0. So it's like it's a way of introducing noise, but noise, it's not actual noise. It's just setting the values to 0. So that's why you could also use Gaussian noise layer in its place, which would be similar in some ways to introduce random values in there instead of dropping into 0. So it's just a different way to help your network converge, because it's a way to help with the randomness of the data. It can you're not always getting the same values through, so it helps your loss function converge ultimately, and helps it be more robust in handling different data.
All right, I think we'll pause there, Jeff.
Okay.
We do have another session this afternoon for further discussion and questions. I'm sure there'll be many more cropping up in the next hour or two. But thank you very much for that very insightful talk. And we'll take a short break now for 10 minutes and be back with the next speaker. Thank you.